I'm Nick Snyder.
And I'm Kyle Stoker.
And this is the controlled dynamics of kicking a football. The two components of our dynamic system are a football and a field goal. The football features a mass of 14.5 ounces, a length in the y direction of 11 inches, and a max circumference of 21 inches occurring halfway up the ball. The field goal features a base height of 10 feet, two 20-foot tall uprights, and an 18.5-foot crossbar in between them. The goal of our system is to successfully kick the football through the field goal. If it is not successful, we can change the kicking motion in order to make it through the uprights. The assumptions of this system is that the ball is rotating purely about the y-axis, there's no drag on the ball, and there's no wind acting on the ball during flight.
The following are the governing equations of motion for our system. The two equations we'll be using in our dynamic control are momentum and kinematic velocity. The momentum of the football is equal to force times the time the force is applied, which is also equal to the mass times the velocity. Using this velocity, we can find the kinematic motion of the system, which in the y direction is Vy equals v times the sine of theta, the initial angle of the ball's trajectory. The x velocity is equal to v times the sine of theta.
The inputs of our system are the force of the foot contacting the ball, the contact height, or where on the ball your foot impacts, and the aiming angle, or the direction of the force on the ball. The outputs are the trajectory of the ball. Does it go through the uprights or not? The measured values are the distance traveled. Does it go far enough? The height of the ball when parallel to the field goal, is it high enough? And the distance from the area in between the uprights, did it miss left or right?
The two frames of the system are shown here. The body frame of the football is depicted on the left, and this frame rotates with the football throughout its trajectory. The inertial frame of the goalpost is on the right, with its origin on the ground directly beneath the center of the crossbar. Shown here is a block diagram of the system with some basic control elements. You start with the football on a kicking tee, input a force, and use the equations of motion to find the velocity and final position of the ball. If the ball missed left or right, you are able to adjust the direction of your kicking, and if the ball fell short of the goal, you can adjust the angle the ball is kicked or add more force.
Scenario 1 is kicking the football at too low of an angle. As seen here, the kicker impacts the ball too high up, creating a launch angle that is unsatisfactory. The ball does not have enough velocity in the y direction to reach the height of the crossbar. On the opposite end of the spectrum is scenario 2, where you kick the ball at too high of an angle. With too steep of a launch angle, the ball has a majority of its velocity in the upwards direction, and thus will not reach the goalpost before landing.
Scenario 3 is missing the kick to the right or left of the goalpost. In addition to having a proper launch angle, you must kick the ball in the proper direction to make the field goal. If not, you will miss the uprights to either the right or left side. A field goal is not always a straight-on attempt, and you must compensate by adjusting the direction you kick the ball. At long last, Scenario 4 is a successful field goal kick, combining a textbook kicking motion, a proper launch angle, and a keen eye for your kicking direction. You can split the uprights every time.